back for dividing radicals. We'll come back to this again and throw some addition in the mix, which will make it even hairier. But for now, this is actually not a whole lot of extra work. You have a couple of options to make things easier, but a lot of the work here will end up being just rationalized denominators, which we did in the last chunk. So the only thing I would say is consider this option. We have a property that says the square root of x over y is the same as the square root of x over the square root of y. And that works two directions. Yes, you can split a square root up, but you can also put one back together. So we're going to say the square root of 54 divided by the square root of 6 is the same as the square root of 54. Saying that isn't very thrilling. Square root of 54 sixths. How about that? I think that worked. The only reason I would want to do this is if I can then reduce the fraction, especially if things divide in evenly, which they do here. 54 divided by 6 is 9, which happens to be a perfect square. So, yes, you can rationalize denominators. You'll get the same answer as if you mush roots together. Sometimes mushing roots together doesn't help you at all. You just have to split them back apart and rationalize denominators, but it's an option to consider. So here, let me switch colors. For example, in this next one, I could mush that together and say, oh, that's root 13 over 5. But then I'm completely stuck because I can't reduce the fraction. And having a fraction under a radical is considered equally as bad as having a radical in the bottom of a fraction. So that's kind of a no-no. Only want to do it if it allows us to get rid of the fraction or at least simplify it, especially get rid of it. So all I'm going to do here is say, okay, well, I'm not seeing anything nice if I put them together. So let's just get rid of the radical in the bottom. So I say I'm dividing radicals, but really this kind of fits in the changing the appearance of radical section. I'm really just kind of changing how they look. Sometimes they work out nicely and you feel like you did division like in the last one, but often they don't. What is 13 times 5? 50 and 15, 65. And root 25 is a 5. So that one entirely ended up being rationalized the denominator. Okay, next one is another one where if you're paying attention, you can rationalize the denominator. But if you're paying attention, you might actually be able to get off the hook. And what I'm seeing is I'm just going to mentally split off a 1/4 and say this is exactly the same as if I had 1/4 times the cube root of 20 over the cube root of 2. Notice, multiplying fractions, we go straight across and get just the cube root 20 on top and the 4 cube root 2 on the bottom. So it really is the same. And the reason I want to do that is because I want to combine the 20 cube root 20 over 2. And again, the reason I want to do it in this problem when I didn't in the last problem is just because the 20 and the 2 actually share factors. I can divide 20 by 2. So without having to rationalize the denominator, I can say, okay, well that's 1/4 the square root of, or the cube root of 10, or whichever of these two you like is fine. These are equally simple. Cube root of 10 over 4. So if you hadn't done it that way, I'm not going to walk all the way through, but I'll show you what would happen. Basically, in the bottom, we're really hoping to build up the cube root of 2 cubed, the cube root of 8. So you'd have to multiply top and bottom by cube root of 4. And you'd get the cube root of 80 over 4 times the cube root of 8, which is 2. And that seems pretty nice, but you're not done because you have to extract roots. So you would then have to say, okay, maybe I will just do the whole thing. The cube root of 80. So looking for perfect cubes, 80 is 8 times 10, and 8 is a perfect cube. If you're having trouble spotting, remember you can go list. 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. So just start a list of the first 2 or 3 until you spot one that seems helpful. And then when we split up, the cube root of 8 is 2. The cube root of 10 is what it is. And then last step, cancel cube root of 10 over 4. And we get to the same place. So you really will get to the same place. I kind of like mushing the roots together and just being able to do the division more than having to rationalize and then extract, but it's up to you. Okay, last one, same idea, but with fourth roots. This is another one where I don't want to just squash it together and say I have the fourth root of 11/3, because I can't do anything with that. So now I'm going to say, okay, I want to build up a perfect fourth power. I've already got 1 3, so I need 3 more. So I'm going to multiply top and bottom by the fourth root of 3 cubed, which is 27. So I end up with 6 times the fourth root of 11 times 27. I'll think about if I want to actually figure that out in a second. And then on the bottom, I end up with the fourth root of 3 to the 4th, with it, which is exactly what I was hoping for, because fourth roots and fourth powers cancel. So I have 6 times the fourth root. Okay, I'm going to try and figure it out. 10 times 27 is 270. 1 times 27 is 27. So 270 plus 27, 297. You guys can double check me and laugh if you want, if I'm wrong. And then the fourth root of 3 to the 4th is 3. This is looking pretty good, but I do need to reduce and say, okay, I can cancel out a 3. So I have 2 times the fourth root of 297. And you might be worrying that you need to extract roots. I am feeling very confident that there are no perfect fourth roots to extract from 297, because I know that 297 is made up of an 11, which is prime, and a 3 cubed. And nowhere in there can I get 4 of the same factor grouped together to take the fourth root of. So to get rid of a fourth root, you've got 4 of the same factor. Okay, so dividing radicals, really kind of a changing the appearance thing. Thanks for watching.